In question 5, we're again looking at vertical projectile motion, where two balls, A and B, move vertically in the presence of the Earth's gravitational field towards the ground. To start off with, we're told that A is dropped from rest from a height of 80 meters. That means the initial velocity of object A is going to be 0 meters per second, and the total displacement it will undergo is going to be this 80 meters. Question 5.1 asks you to calculate the time taken for ball A to reach the ground. Again, we're going to need a direction convention. I'm going to stick with up as positive, because that's the usual convention with the y-axis, where y pointing up is the positive direction. Let's take a look at the starting information that we have. The objects are in free fall, we're ignoring air resistance, so the acceleration must be the acceleration due to gravity, negative 9.8 meters per second squared. We do know that the initial velocity of object A is 0 meters per second because it's dropped from rest. And we know that the displacement undergone by object A is this 80 meters. But let's take a look at these signs, and it's important to pay attention here to the signs, and this is where most of you actually went wrong on this question. If up is the positive direction, that means the acceleration must be negative because the acceleration is down. If up is the positive direction, your displacement must be negative because your object falls down by 80 meters. So what you need to have is a negative 9.8 over here and a negative 80 over here. Those of you who got this question almost right probably had an inconsistency in your signs here. Either your negative 9.8 you actually had as positive 9.8, or more likely you correctly put down negative 9.8 consistent with up as the positive direction, but you incorrectly put down 80 meters rather than negative 80 meters. You would have found that you still got to 4.4, but only by taking the square root of a negative number, and you basically ignored the fact that it was negative and you just took the square root anyway. That should have been your first clue that you'd made a mistake. Negative 9.8 needs to be matched up with negative 80 in this question. Let's move on to question 5.2. In 5.2, you're told that ball B is thrown down from the same height, and it's done 1.5 seconds after ball A is released. You are asked to calculate the magnitude of the velocity with which ball B must be thrown in order to reach the ground at the same time as ball A. Again, I'm going to take up as the positive direction. We need to take a look at the information that we have. If up is positive, gravity is still, or gravitational acceleration rather, is still negative 9.8 meters per second squared. The displacement of object B, it's still negative 80 meters because it has to reach the ground and it was released from the same height. The only difference is that object B was thrown down, so it was released with a non-zero velocity. In which case, we need to choose a formula that relates the known information, the acceleration due to gravity, the height, or the displacement, the negative displacement undergone, and the time that we're told about. We're told about this 1.5 seconds. Now, 1.5 seconds is the time after ball A is released, which means the time that ball B actually is in the air is 1.5 seconds less than the time ball A was in the air. Ball A was in the air for 4.04 seconds. We just found that in question 5.1, which means we need to subtract 1.5 seconds from 4.04 seconds to get 2.54 seconds, which is the time difference, which is the time that ball B was actually in the air. The relevant equation of motion is this one over here, which tells you your displacement in terms of initial velocity, time interval, and acceleration. Substituting these values in, paying attention to the negative 9.8 and the negative 80, gives us a magnitude of 19.04 meters per second. When you actually do this calculation, you'll find that it's negative 19.04 meters per second, and that's consistent with choosing up as your positive direction, which tells you that a negative initial velocity must be pointing down, which makes sense. The object needed to be thrown down in order to be able to catch up with object A. The question asked for the magnitude of velocity, which is why we would just leave this as 19.04 meters per second without the negative sign. In question 5.3, we're again performing a relative velocity calculation. What we need to do before getting properly into this calculation is determine the velocity of A at the time that ball B is released. Ball B is released 1.5 seconds after ball A is dropped. So that means gravity has 1.5 seconds to act on this ball, 9.8, acceleration due to gravity, multiplied by 1.5 seconds, to give us a change in velocity of 14.7 meters per second. So the change in velocity of object A is 14.7 meters per second. That's where this number comes from. Object B, we've worked out, was released with a speed of 19.04 meters per second. In this particular case, I have taken down as positive simply to not work with too many negative numbers. It's perfectly possible to do this calculation with up as positive as well. The relative velocity between A and B, or the velocity of A relative to B, is the velocity of A minus the velocity of B. Putting the 14.7 that we've just calculated, was a pretty quick calculation, into this formula, subtracting 19.04 meters per second, which was the speed of B, the velocity of B going downwards, remember we're treating down as positive here, gives us negative 4.34 meters per second. And if down is positive, a negative relative velocity must be pointing up. In this particular question, 1 mark was for getting the magnitude of 4.34 meters per second, and another mark was for correctly getting the direction of the relative velocities. In question 5.4, you're asked to think about whether or not this relative velocity of 4.34 meters per second up will change. Would it increase, decrease, or would it remain the same? You need to think about this one quite carefully. A large number of you actually got this question wrong. The relative velocity will stay the same. The important thing to realize is that both objects experience constant acceleration. They experience the same acceleration, which is the acceleration due to gravity. If acceleration is constant, the change in velocity must be constant, so the velocity difference must remain constant as well. Yes, the velocity of object A does change. The velocity of object B also changes. But the relative velocity, or the velocity difference, that does not change, so the relative velocity must remain the same. That means that the relative velocity between object A and B remains 4.3 meters per second up throughout the motions of A and B, up until one of them hits the ground, and in this particular problem, they both hit the ground at the same time.